Often these guys have like a 30 section. They're like, listen, I think we're gonna look in our catalog and see. Yeah, this person did a PhD in mechanical engineering or controls specifically. Okay, maybe to like $100 they need to try. I'll give you some of those. That's allowed to take this.
All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Good, good. All right. So we're week 10 right now, and so it's I know it's a big week in this class because we have our midterm projects due. So remember that's due on Friday. And so this week I'll be available most of this week, and so I'll be staying after class to answer all your questions because I know this is kind of crunch time for the project, and so wherever you are in the project, don't be afraid to ask a question, and I'm always here to help with that. Okay? All right, and so for today, we're going to pick up where we left off about 2 weeks ago, actually. And so if you remember from 2 weeks ago, we were talking about advanced meshing in ANSYS. And so today, we're going to pick that up. And so last week we took a break just so that we could do the activity and that we can learn about transient simulations. But now we're kind of back to talking about meshing. And then this week we're going to continue on and start to talk about non-linearities in in finite elements too. Okay, so what that means and how do we account for that in our finite element simulations. Okay. All right, and so with that said, are there? I think that's the only announcements I have. Are there any questions I can answer? Okay, all right, so let's go ahead and get started. All right, and so this is all, this is kind of a resume of what we were covering 2 weeks ago on advanced meshing. All right, and so the idea with this advanced meshing topic is to kind of cover, what I think are all really important information with regards to meshing that you should know as kind of advanced users of ANSYS. Because my goal with this class, as with same as the undergraduate, but but you guys are more advanced because you're graduate students, is I want you to leave this class with the confidence that you can apply ANSYS to any problem that you could feasibly do it for any professional application. Okay? And so part of that is kind of having a good understanding or deep understanding of all the different meshing settings that are available to you that are used for kind of a normal problem. Okay. And so we're not going to cover every little meshing function that there is or every little meshing feature because with kind of the history that ANSYS has, there's so many features in it that are so niche that they may only have one very specific application. And so we're not really going to go into any of those cases, but I want to cover all of the settings and all of the features that that I would consider to be kind of a typical that kind of work its way into kind of a typical finite element workflow. Okay, and part of that is the meshing, because there's a lot that we can go over here. Okay? And so last time what we left off with is a discussion of what are how do the different hexahedral measures work, and what do terms like patch conforming and patch independent mean. Okay, and so what I want to pick up on today is I want to talk again about how do we rate the convergence behavior of the different elements. Because convergence, we've already talked about convergence, and the idea with convergence is that convergence has to do with the fact that you want to get your mesh to a point where if you refine the mesh any further, then the solution doesn't change or doesn't change significantly. Okay. Right. And so you just got some practice doing this convergence test in activity 4. And so when you did this mesh convergence test, that's kind of what you were looking for, right? And so the idea with convergence is that if you make a plot like this, okay, where on the x-axis you have some metric for how refined your mesh is. So typically this could be something like the number of elements that you have in the mesh. Okay, and on the y-axis here you have the value of some quantity of interest. Okay. All right, and generally, generally speaking, you should want a situation like this, right? And so maybe for a fairly coarse mesh, which doesn't have that many elements, your solution might start here, but then as you refine the mesh, you reach a point where this convergence plot kind of plateaus. Okay. And so typically speaking, you want to be in this area, right? Because once you're in this area, then any further refinements of the mesh don't improve the solution at all. And so, we say that the convergent plot has kind of flatlined. Okay. And so in activity 4, we took a look at a specific case of we kept all the other meshing settings fixed, but only just varied the size. And this is kind of what you saw or what you're supposed to see. Okay. And so, the reason we're talking about convergence is that, when you change different properties of the elements, and so when you change its element order, when you change the element shape, then it affects the shape of this convergence plot, okay? Okay. And so ideally what you would want is you would want to achieve convergence with a less number of elements. And so that's kind of the idea, okay? And so if you could change the mesh setting such that you achieve convergence like this, right? And so let's say that your convergence plot has a steeper incline, okay? And it reaches this flat line value faster, okay? Okay. And so in the purple case, let's say that we achieve convergence, maybe around there, okay? This is obviously a lot more desirable because you end up with a mesh with a accurate result, but you did it with a lot less elements. Okay. And so, what I want to talk about is, as you change things, like you change the shape of the element, right? You go between tetrahedra and hexahedra. You change the order of the elements. You go from linear to quadratic. And so I want to talk about generally what you can expect for the convergence behavior. Okay. And so that's not to say that, the plots that I'm going to show you, that's not to say that they apply universally, but they're good for general trends and what you can kind of generally expect. But of course, each situation, each simulation is kind of its own thing. And so, you might not get exactly what I get here, or sometimes you might get the opposite. That's true. But generally, I think you should have an understanding of, what, if you make certain decisions with your mesh, how that's going to affect your convergence. Okay. All right. Any questions on this? Okay. All right. So let's talk about some of those convergence behavior. Okay. So we did talk about this 2 weeks ago, but I think we kind of rushed through it a little bit. And so I want to make sure that we kind of really go over, because I think this is kind of one of the most important points from the set of lecture notes. Okay. All right. And so the data that was used to produce these plots was for actually a very simple case. And so the case was a cantilever beam. Okay. Okay. And so I'll admit, this is not the best case for this because it's so simple. And so realistically, you would want to do this for a more complex case so that you have the complexity of the situation adds to it. But I think a simple case is fine for what we're doing. Okay. And so, we have a situation like this where we have a beam that's fixed to a wall. Okay. And so we have a fixed constraint here on the left side, and then we're going to be placing a load on top like that. All right. And so the first comparison that we're going to look at is doing a comparison between linear hexahedra and linear tetrahedra. Okay. Oh, and of course, this is static structural, and so we're doing a structural simulation. Okay. And it's all static, and so we're not doing any unsteadiness. All right, so let's look at the convergence plot between these two types of elements. Okay, and I believe the quantity of interest that they look at here is the deformation of the tip. Okay? And so they're looking at, or they're measuring how much the tip of the beam is deflected. Okay? All right, let me draw the plot for linear tetrahedra first. Okay, so this is going to be the first one that we look at. And so the plot for the linear tetrahedra starts down here. Okay? And it goes kind of like this. Okay? Where this low point right here is about 0.3, I think 0.3 centimeters. Okay. And so I unfortunately didn't write down what they have for the load, but the load is such that, for that low number of elements, you get a deflection of about 0.3 centimeters. Okay. Whereas the converged value up here, this is around, I would say 0.68 centimeters. All right, and so that's the plot for linear tetrahedra. And you can see that we have a huge, difference, right? And so we actually start out with something really low, with something that's less than half of what the converged value should be, right? But as you refine the mesh, the solution gets better. All right. And so let's compare that to linear hexahedra, okay? And really this is not really kind of a fair comparison, because what you'll see for the linear hexahedra, the linear hexahedra does converge too, but it starts out so much closer to the converged value that it looks like it's already converged, but it's, if you compare it to how much the linear tetrahedra have to go, the linear hexahedra kind of just looks like a straight line, okay? Okay. And so not really a fair comparison, because in reality, it is converging. And so there is kind of a section here where it's down lower, but it's so much smaller, or that gap is so much smaller compared to the linear tetrahedra that visually you don't really see, okay? And actually, the converged value that you get for the linear hexahedra is a little bit higher. And so that converged value is 0.7 centimeters, okay? And so even at the converged value, right? So even when the linear tetrahedra reach convergence, it's actually lower than what the converged value is for the linear hexahedra. Okay? And in terms of accuracy, this is going to be the more accurate one, okay, or the more reliable number. Okay. All right. And so what conclusions can we draw from this figure? Oh, question.
Oh, I was actually going to ask a question.
Yeah.
So why is it that the tetrahedra, or the hexahedra, is it because they model that shape so much better than the hexahedrons that it reaches convergence so much quicker?
Yeah, that's part of that.
Okay.
But the other part, so remember when we were going over all the different element types and we listed out the interpolation function? The hexahedra, the linear one, had all of these cross terms. And so it had terms like x times y, it had y times z, it had x times z. And so those make a really big difference in these cases, because then they're allowed to model these kind of non-constant stresses. And so what's happening in the linear tetrahedra case is that there's a bunch of shear locking going on. Yeah. And so remember, shear locking is the phenomenon that if you do a structural simulation with a linear tetrahedra or a linear triangle, then you can underestimate the deformations by quite a bit, because you have this phenomenon where the stress inside the elements is constant. Okay, where the simulation relies a lot on stress variation as you go through the element, and so because we have the shear locking, then you have the deformation is kind of almost severely underestimated. Okay. And so kind of the upshot, or kind of the conclusion from this graph, is that linear tetrahedra are bad, okay? Okay. at least for structural simulations. Okay, and so you know, this is something that, you know, we've talked a lot about already, and so, you know, we all kind of know this. But here you can kind of see the hard data, where even for like a very simple case where you have just a beam, you're just putting a load on it, and then you're seeing what the deflections are. And so even for this really simple case, you know, the tetrahedra have to work so hard, you know, just to even get close to what the converged value is, right? And so unfortunately, you know, I didn't write down what these numbers are, but, you know, you can imagine that, you know, to reach this point where it is actually converged, you know, this might be on the order of, you know, maybe like 70,000, 80,000, 100,000 elements, okay? Okay. And for such a simple case like this, like 100,000 elements is kind of absurd for, you know, what you would need to get a converged solution. And so, you know, with linear tetrahedra, you know, it is possible to make them work for structural simulations, but, you know, you have to refine it to such a degree where it's just not practical most of the time. Okay. All right. Any questions on this? Okay. All right. So that's the comparison between the linear tetrahedra and the linear hex. Okay. Now let's look at the comparison between the quadratic tetrahedra and the quadratic hexahedra. All right. So this is a little bit of a more fair comparison. Okay. All right. So we'll make the same plot. And so on the x-axis, we'll have number of elements. And on the y-axis here, we're going to have tip deflection. Okay. All right. And so let's look at the quadratic tetrahedra first. Okay. And so for the quadratic tetrahedra, it's going to look something like this, which, you know, visually, you know, might look the same as what we just drew on the previous page until you actually look at the values. Okay. And so the starting value here, if you remember for the linear tetrahedra, you know, we're starting with something that's really low. And so we started with about 0.3 centimeters. Okay. Here, you know, we have a starting value of 0.74 centimeters. Okay. And so, you know, we're starting a lot closer to what we actually want. Okay. And this converged value up here, you know, it's not all that different. And so it's only 0.75 centimeters, right? And so the difference in between, you know, what we consider the non-converged value and the converged value is really small. And so, you know, even with a fairly coarse mesh, you know, if you're going to use a quadratic tetrahedra, you know, you're still going to get fairly close. Right? But of course, you know, the quadratic hexahedra are going to outperform it just by a little bit. But the difference here is not that severe. And the difference you only really see at lower, you know, lower element magnitudes. Okay. Okay. And so for the quadratic hex, you know, we can see here that we reach the same converged value of 0.75 centimeters. You know, we just do it a little bit more quicker than the quadratic hex. Okay. And so this starting point right here, this is maybe about 0.747 centimeters. Okay. And so we start out a little bit closer at a coarser mesh, but, you know, we quickly converge on the right one, you know, within no time at all. Okay. Right. All right, so a couple observations from this plot. And so first observation, you know, clearly, you know, even if you're doing a tetrahedra, a quadratic tetrahedra here, you know, seems fine. Okay. Okay. And honestly, for a lot of more complicated projects, just kind of the reality is you're going to be working with tetrahedrons because, and for for the project, probably many of you are experiencing this too, is that no matter how hard you try on a geometry that may seem like you can do hexes on it seems simple enough, ANSYS sometimes just refuses to do it. Okay, and so sometimes you're just kind of forced through ANSYS to just use a tetrahedron mesh. But even though we talked about how it's not ideal, you can still see here it's pretty good, and so you're not really sacrificing anything by using a quadratic tet. Okay, and so the only thing to make sure is that you just make sure that your element order is quadratic. Okay, but you can see here that it performs really, really well. Okay. All right. The other observation I want you to take away from this is to compare the converged values for the deflection to the linear cases on the previous side. Okay, and so if you look at the previous graph, you can see that the converged value was about 0.7 centimeters, right? And so here we reach a little bit of a higher converged value. Okay. Okay. And the reason for this again is shear volume, right? And so even though the linear hexahedra, it does combat shear volume quite a bit, it still never really fully escapes from it. And so in the quadratic case, that's the only place where you can really truly say that shear locking is not an issue. Okay. And so this is the reason why that when you're working with when you're doing a structural simulation, you almost always you're going to be doing a quadratic mesh, right? I can't even think of a situation where you would use a linear mesh. The only situation where I think you would use a linear mesh in structures is if you have a large portion of your structure where you don't really care about the solution there. And you can afford to kind of coarsen that up because linear meshes are cheaper on a per element basis. And so if that were the case, then you can use linear. But for any part of your model where it's going to be supporting loads or getting some deformations or getting some stresses, you want to use quadratic there so that you eliminate this this factor of shear locking. All right, any questions? Yeah.
Yeah, so for a mesh convergence test like this, when you have multiple sizing objects, is all we ever care about the number of elements when it comes to that? And we just kind of have to like play around with the number of elements in each separate sizing object and see how it affects the curve or total number of elements?
Mhm.
Okay.
No, it's a good question. So normally where you'd want to add the refinement are the places where you have kind of high stress concentrations, right?
Okay.
And so normally the only, when you make a graph like this, the only thing you're really changing is those areas.
Okay.
Especially if the quantity of interest that you're measuring is within that area. And so that's really the only thing that you'd be refining. Sometimes you might have a quantity of interest that spans kind of multiple parts of your geometry. And so maybe you're looking at kind of the overall average stress in the whole geometry. And so in those cases, you would refine multiple places. But most of the time when you perform refinement, it's only in those kind of select regions where where you have kind of interesting behavior.
Okay, so
Yeah.
should we just like turn on the max value thing on ANSYS, kind of see where our red is, and then just focus on that, and that's it?
That's definitely a good approach.
Okay.
Yeah. Mhm. All right. Any other questions on this? Okay. Actually, one more thing I want to point out before we move on to the next page is that, our quantity of interest here is deflection, which is basically the same thing as deformation, right? If you notice, I'm always drawing these curves as coming up from below, right? Or in other words, we're starting from, a lower value and then rising up to a converged value, okay? And actually, if you look at the mesh convergence plot that I gave you in activity 4, the sample one I gave you in the problem, that was also for deformation. That one also approached from below, right? And so that's kind of typically the behavior that you would expect from this. Okay. Because what typically happens for a coarser mesh, and so the more coarse your mesh is for a structural simulation, coarser elements add what's called artificial stiffness. Okay. And so because the elements are so big, they add kind of some, I would say kind of art, you can think of it as artificial, it artificially raises things like the Young's modulus. It artificially, creates kind of more stiffness within your structure where it's harder to deform, okay? And so as you refine the mesh, this factor or this kind of artificial stiffness effect goes down naturally. And so that's why, as you refine the mesh, it always kind of approaches convergence from below, okay? And so just a little bit of trivia, as you do mesh convergence tests, and I promise you, if you work with finite elements professionally, you'll be making a lot of these plots. What you'll see is that the deformation always approaches from below because of this effect. Okay. All right. And so the last comparison that I want to do, because the last 2 comparisons that we did were just between the 2 different shapes, right? And so we did tet versus hex on both a linear scale and a quadratic scale, okay? And so the last comparison I want to make is between linear versus quadratic. And just so that the comparison is fair, we'll do it for hexahedra versus, instead of tetrahedra, okay? All right, so this is going to be linear hex versus quadratic hex. And so, all of the same trends that we talked about before are going to apply here. And so you would expect that the linear hex is going to take longer to converge, and the convergence value is going to be lower than the quadratic one. But it's actually not that far, right? And so if we look at the linear hex, the convergence might look something like this, okay? Where the low point here, I think is around 0.65 centimeters, okay? And the converged value up here is the same as it was before, 0.7 centimeters, okay? Whereas the quadratic hex, the convergence might look something like this. It's a little bit too generous. It might look something like this. Where once again, the converged value for the quadratic hex is going to be around 0.75 centimeters. Okay. And so, all the same trends that we saw before are kind of on display here, where, for the linear hex, it does a pretty decent job. And so it doesn't do a bad job here, but, we're always going to have this gap right here, because of the shear locking effect. Okay. And And just because of the fact that it's linear, it reaches convergence a little bit slower than the quadratic one. But all things considered, a linear hexahedra is not bad, and so it performs pretty well. But most of the time, again, you're not really going to be using linear hexes. But I did want to show you this plot just kind of for the sake of completeness for this. Okay. All right. Any questions on this stuff here? Yep.
So let's say like in a real life situation, because you said like with the dynamics stuff, we have to use linear elements because
Yep.
of cost. Is there like a set % difference with linear versus quadratic hex? Like, so we can say, like if we did a dynamic simulation, oh, we use linear hex, so expect a plus or minus, probably more like a plus 5% or minus 5% difference.
Unfortunately not. And so it's that difference is going to be different for every situation because it depends on the magnitude of the loading and a lot of geometric features too. And so actually the next set of lecture notes will be really relevant towards that because because our next set of lecture notes is about nonlinear effects. And so you're talking about nonlinear deformations, nonlinear materials and things like that. And generally speaking, when you go into dynamic situations, the nonlinear effects kind of get amplified a lot more. And so for a lot of static situations, actually, nonlinearity, it can make a difference for certain situations, but it's oftentimes not as big. And so using linear elasticity and like we have been doing is actually not bad for static situations, but for dynamic situations, you have to account for a lot of those for nonlinear effects. But yeah, we'll cross that bridge when we get there. Yep. All right, question. So do convergence of different properties like deformation and stress occur at same number of elements? No, that's a great question. And so generally the convergence of deformation is going to be a lot easier than for stress. Because deformation is a primary variable. And so that's kind of the first thing that ANSYS is going to solve for. And then based on the computed deformation field, then it computes the stresses from there. And it uses things like derivatives. And so, if you kind of repeated this exercise with the stress, you'll see that the convergence is probably going to happen more towards the right. Because derived quantities like stress, excuse me, is a lot more difficult than for primary variables like deformation. Yeah. Mm-hmm. All right.
I'm sorry.
Oh yeah.
Just based on that. So like if yield strength or something like that is something that we're really concerned about, should we do our convergence test based on that instead of something like deformation?
Definitely. Yeah. So you always want to do your convergence test on the quantity that's going to be most difficult to converge.
Okay.
Yeah. Yeah, that's a good point. Let me write that down. Okay. And so for cases where you're interested actually in multiple things, and so a lot of times you're interested in deformation, you're interested in stress, you're interested in these quantities at different locations in your geometry. And so at the very least, you should do a convergence test on the most difficult of those quantities. But it also doesn't hurt to do a convergence test for all the other things as well. Okay, it's a little bit tedious. It's kind of a lot of work, but it's if you can show convergence for everything that you're reporting on, or at least the quantities that's relevant to the design, then that's a pretty thorough verification of of the reliability of your results. Okay. And so it's a lot of work, but it's useful to do. The more quantities that you do convergence on, or the more quantities that you're interested in, the more reliable your results are going to be in general.
I'm sorry.
Yep. Oh, no problem.
So if we have something that's like stress that's more difficult to converge than something like deformation, can we just say like are stress converged, so for sure deformation.
Generally, you can say that, and generally, I think you would not be incorrect. But then there's some weird things that can happen in the model too, where they're not going to be correlated, especially if you're interested in deformation in one place and stress in another place. And so, if that were the case, just because you converge stress here doesn't mean you can converge deformation over here.
Okay.
Yeah. But if they're in the same location, I would say that you can just do one. But if they're in different locations, I would say you should do them separately. All right. And so that's convergence behavior. Okay. And so the last bits of the advanced meshing notes are kind of more advanced meshing features in ANSYS that you can try out. And so my plan right now is to not explicitly make you all try these features, but they are available for you if you want to try them out. And so I wanted to introduce them to you and talk about what they all do and what you can expect from them. Just so that you can try them out if you want. But right now, these features are pretty advanced, and so I don't think I'm going to make it a requirement because it's you don't have to do any of these things for sure. Okay. All right. So first thing I want to talk about is defeaturing. All right. And so the idea with defeaturing is that ANSYS has the ability to kind of automatically suppress some really small, tiny features in your geometry. Okay. And the reason you would want to do this is that those small tiny features are going to create a nightmare for your meshing. Okay. Okay. Because the thing with those small tiny features, and so what I mean by that is, let's say that you have a kind of a surface like this, okay? And so let's say that we're kind of looking over the top of the surface. And so let's say that you have some kind of small, surface features where, their purpose mostly is just cosmetic, right? And so let's say that you have kind of a channel, a very tiny channel. And so let's say that, you have a channel like this, or this might be some kind of lettering or some kind of, something that's imprinted on the surface of your geometry. Okay. And so if you looked at it head on, it might look something like this, where you have kind of a rectangular plate, and then maybe you have kind of a small circle here that's kind of imprinted, into the surface. Okay. And so this shaded area here it's not a cut, and so it's not a full cut through the geometry, but it's just kind of a small kind of maybe laser cut imprint on the surface. Okay. And so the thing with small geometrical features like this is that they don't really add anything to the structural integrity of the system. They also don't really take away from it. Okay. Okay. And so they're not really doing anything to to improve the structure, but what they are going to do is it's going to make meshing a headache for you. Okay. Because what ANSYS sees, especially when you go to do automatic meshing, even when you specify the size, right? Because if you notice, when you specify a sizing object in your mesh, that's the maximum edge size that it can use, right? But it does give ANSYS the liberty of making meshes that are smaller than that, okay? ANSYS will always try its best to, to respect your edge size as much as possible. But what can happen sometimes is that if it sees tiny features like this, it sees that, oh my gosh, this edge right here is so tiny, right? I can't fit a big tetrahedron there. And so what it's going to do is going to make a really tiny mesh in this area. Okay. Okay. And so that means that everywhere around your indent, okay, you're going to have a really refined mesh, right? Without you really doing anything about it, okay? And so you're going to have all that mesh density there, and it might be in an area that you don't really care about at all, okay? And you can't really control, the sizing there. And so even if you try to force ANSYS to make a bigger size there, because these geometrical features are so small, ANSYS is just naturally going to put a smaller mesh there, right? And so this is always a nightmare to mesh, okay? And so what ANSYS does is that, it has this idea called defeaturing, and there's kind of multiple ways that you can implement it, where you can tell ANSYS to automatically, ignore cases like this. Okay. Question. So would the bearing shaft for the midterm be a good candidate for deep featuring just because it has small grooves? Yeah, actually both geometries for the midterm project, it has a lot of these small features that can be defeatured. And so I think both of them have a bunch of bolts and a bunch of nuts that can be defeatured. And a bunch of them have smaller curves like that can work like that too. And so, I gave those to you on purpose so that you can, that you can see that in action. One thing you can always do is you can always manually defeature. And so you can always manually suppress these parts. I think that's what most of you are doing. And so most of you are kind of manually suppressing the nuts and the bolts so that you don't have to worry about meshing them. But ANSYS does have some automatic features. Before we kind of talk about this further, I wouldn't rely on this a lot. I wouldn't just rely on the automatic defeaturer to get rid of all these things. If you can manually get rid of something that will cause you issues, get rid of it, right? So don't rely on ANSYS to do that for you. But there are some automatic tools to detect things that maybe that you can't manually get rid of yourself, and that's kind of the point of this defeaturing. Okay. And so this is especially true, when you're doing a patch conforming method. Remember, when you use a patch conforming method, then the ANSYS mesher is going to respect the boundaries of your geometry perfectly, right? And so all features that you have, it's going to be modeled perfectly with patch conforming. Okay. Okay. Right. And so that ends, and because that's the point of patch conforming, so that your mesh patch conforms to your surface perfectly. Okay. And most of the time you're going to be running with this because that's the default, and I would say generally that's the more generally recommended option. But the first kind of level of defeaturing that you can do is that you can switch it, and so instead of doing patch conforming, you can do patch independent instead. And so that's kind of the first level of defeaturing that you can do. And so you can say that, more so than, retaining every single tiny feature on the surface, you're more interested in, you're more, you prioritize more a higher quality mesh with, elements that are not clustered in these kind of small geometric features. And so, that's kind of the first thing that you can try, where if you have kind of a particularly challenging geometry, where you have these small features that you can't manually suppress yourself, try switching it to patch independent. because patch independent, like we talked about before, will build your mesh from kind of the inside out, and it'll prioritize higher quality elements more so than geometric faithfulness. Okay, and so that's kind of the first simplest thing that you can do, to make sure your mesh quality is good. Okay. Question.
Is there a significant difference between the convergence behavior for patch conforming and patch non-conforming?
Yeah, no, it's a good question. And so, yeah, so generally, because with patch independent, you'll get higher quality elements, and so you're much less likely to get skewed elements. The mesh convergence will generally be better for patch independent, because you're going to have a higher quality mesh. But if your convergence depends on one of those tiny features being modeled accurately, then you might actually get better convergence with the patch conforming method. Because with patch independent, if you refine your mesh, what happens actually each time that your geometry actually changes a little bit, because it's not really caring about the boundaries all that much. And so if you refine the mesh, that's actually going to change your geometry, and so that can make your convergence behavior do weird things as well. Yeah, so it depends on the situation, but generally speaking, I would say patch independent is better conversion. All right. Any other questions on this? Okay. All right, and so let's talk about a couple other tools that are available in ANSYS. Okay. All right. And so another tool that's available is something called virtual topology. And so virtual topology, this is really useful in cases where your CAD geometry just has a lot of extra edges that you don't really need. Okay. And so the classical example of this at work is if you have a curved geometry, right? And so let's say that you have something that kind of looks similar to an airfoil, okay? Right, and so this kind of inner surface that I've drawn here, that whole thing is curved, okay? And so what can happen is that just because of the contour and the curvature of the airfoil, you might have situations where you have a bunch of edges that kind of line the bottom here, okay? And these are kind of necessary in the CAD process to kind of get the exact curvature that you want, okay? Okay. And so what can happen then is if you try to mesh this straight up, especially with the patch conforming method, then ANSYS is going to respect all these edges, and it's not going to have any elements that cross over an edge. Okay. Okay. And so, if we kind of draw triangles on this, it might look something like this, right? Right. And so, it'll create a mesh, but the mesh might look a little bit janky because, you'll have kind of these natural kind of ugly lines that kind of run through the, run through the mesh where no element can cross over that. Okay. And so, if you draw kind of the whole mesh on this, it might look, a little bit unnatural, and it might add a lot of cost in your simulation as well. Okay. And so with virtual topology, this is kind of an automatic tool where it kind of looks at a surface like this, and it sees that, we can see that the surface has some curvature, and there's a lot of extra lines here. Okay. And so what virtual topology will do is that it will basically eliminate all these extra lines. Okay, so any line that that ANSYS determines is not necessary for defining the geometry well, it's just going to get rid of them. Okay. Okay. And so that's a big benefit, because now with that removed, then the mesh is not as constrained as it was before. And so if you create a mesh on this, then there's not all these extra edges that are constraining the the elements of the mesh. Okay. And so you're going to get a much cleaner mesh across the surface. Okay. Okay. And so if you're wondering on how to access virtual topology, this is actually a geometric tool. And so this is not something that you access from the mesher. And so this is accessed from the geometry kind of subtree in ANSYS Mechanical. Okay. And so in other words, you can right click on geometry in your in ANSYS Mechanical, and you can click virtual topology there, and you can kind of experiment with that. Okay. And so one place where you can actually try this out is if you're doing the globe valve in the project. I would say this is kind of a good place where you can try it out, because the globe valve has a lot of kind of fillets on the outside, and that creates kind of a lot of edges on the outside of your globe valve. And so if you want to test out virtual topology, I would say that's a good place to try it out, just so that you get a much cleaner exterior mesh on the outside of the globe valve. Yeah, for the bearing housing, I don't think it'll be that as helpful. Even though the housing itself has some curved edges, I think you actually need all of those edges to define the geometry. But for the globe valve, I know that there are some edges that you can kind of get rid of to make a cleaner mesh if you can. Yeah. It makes applying boundary conditions a little bit easier too, because then you don't have to click on so many surfaces. Yeah. All right. Any questions on this? All right. So that's virtual topology. And so another tactic that you can do is called automatic mesh-based defeaturing. And so this is accessed through the meshing tool in ANSYS. Okay. All right. And so the way this feature works is that you specify a length, right? Okay. And then what this does then is that after you specify the length and you tell ANSYS to go produce your mesh, if it ever finds some geometric feature, or it finds some place where the mesh size has to be smaller than this length, it will try to automatically get rid of that feature for you, so that you don't mess up your mesh. Okay. All right. and so if you, if we took the kind of the example that we started out with, where you have kind of that imprint on your geometry, right? If you specify your automatic mesh-based defeaturing to be a length that's greater than the imprint depth, then in theory, this would get rid of it. Okay. I will say that I've tried this out. I haven't had the most success with this, and so maybe it's just I'm not that experienced with it. But I did want to make you guys aware of it, that this does exist. But I haven't really used it for anything practical. It's more something that I've kind of looked at the feature. I've kind of looked at how it works. I've tried it out, but I haven't had the most success with it. But that doesn't mean it doesn't work. I mean, the reason it's in the software is that it works. But I wouldn't be the best source to help you debug that stuff. But I know that this is used fairly common because it is in the textbook. Okay. All right. Any questions on this? Okay. All right. And so the last thing I want to talk about, before we close the lecture on advanced meshing is more refinement options. Okay. Because mesh refinement is something that you're almost always going to be doing in any finite element simulation, right? And so you're always going to be refining the mesh in certain areas compared to others, and so it's good to know what other options there are available to you. Okay? Because so far, when you apply refinement, you either have to do it on an entire body, on an entire face, on an entire edge, right? And so you can either do that by specifying a different sizing object, or you can try the actual refinement object. Okay. But either way, you're kind of limited to the geometrical features of your geometry itself. Okay. And so if you don't have an edge, in a place, or you don't have a good surface in a place where you want to add refinement, you're kind of stuck with it. Okay. And so with these options, it kind of gives you a little bit more flexibility on adding refinement to certain areas and having a little bit more control on the refinement, as well. Okay. Okay. All right, and so the first one I want to talk about is called sphere refinement. Okay. And so in sphere refinement, the way it works is that you specify a sphere, and so you kind of draw a sphere within your geometry, and so you have to give two things, and so you have to give the location of the center of the sphere and the radius of the sphere. Okay. Okay. And so once you've located your sphere, and so the sphere is not something you're physically drawing, and so you're not adding to your geometry at all, and so it's almost like a phantom sphere. And so the only thing the sphere is there for is to specify, basically to kind of highlight a region. Okay. And so what you can do after that is you can then specify a mesh size. Okay. And then once you specify a mesh size, then all of the mesh inside that sphere will have that size. Okay. Okay. And so this is really useful for, when you want to add refinement to a specific region, but you don't have a good surface that you can kind of click on. You don't have a good body that you can click on. And so what you can do instead is just add a sphere to the region, and then you're good to go. Okay. And so I'll draw what that looks like on the next page. Before I do that, are there any questions on this? Okay. All right. Actually, let me draw a situation that actually one of my grad students is working on. And so he was doing a fluid simulation. And so it's not structures, but the idea is the same, where the fluid is kind of entering into this really small orifice, into a very small kind of opening. And so basically the situation was that he kind of had a sphere, kind of a cylindrical area. And then suddenly the fluid comes out into this small kind of jet area right here. Okay. And then after that, the fluid kind of expands after that. Okay. This area right here where the fluid comes in, this is going to be an area of kind of really intense turbulent flow and kind of really interesting velocity patterns. And so it's kind of the fluid mechanical equivalent of an area with a very high stress concentration. Okay. Of course, since this area here is really interesting, we wanted to have a more refined mesh there. Okay. But there wasn't really anything that we can click on around here to kind of specify that area. And so what he did was that he used this kind of sphere refinement. And so he drew a sphere. It looks like this. Okay. And so he kind of specified a region with the sphere. And then everything in the sphere is going to have a smaller mesh size. Okay. And so another name for a sphere like this, and I think this is the name that's actually used in the ANSYS software, is called the sphere of influence. Kind of a silly name, but that's what it's called. Okay. ANSYS has a lot of silly names for some of its features, and so I know there's another feature called pinballing. And so that's kind of another feature that we'll talk about that once we get to nonlinear stuff. But a lot of kind of silly names in ANSYS. And so again, this works great if you want to refine the mesh in a specific region, and you can't really click anything around there to kind of give you that region, right? And so the best thing is just to apply a sphere and then refine everything inside that sphere. Okay. All right. And so the last type of refinement that I'll talk about is called inflation, okay, which personally I think is a terrible name for this, but I'll go with the name that ANSYS gives to it. Okay. And so inflation, this is kind of a way to specify mesh refinement in layers. Okay. And so you can almost think of it as a more customizable version of normal mesh refinement. Okay. Okay. And so what I mean by that is, let's say that you have a particular region, right? So let's say you have a geometry like this, right? And you want to apply mesh refinement on the inside of this geometry, okay? What inflation will do is that it'll allow you to define, how many layers of refinement that you actually have, okay? And so let's say that, you want to apply the refinement in 3 different layers, okay? And so what inflation will do is that it'll say that, you apply a refined mesh like this. That's 1 layer, 2 layer, 3 layer, okay? And so let's say that, you have a refined mesh like this, okay, where you have 3 layers kind of penetrating into the surface of a refined mesh. And then after that, you have kind of your regular mesh after that. And so, let's say that you have mesh, that looks like that. Okay. just like that. Okay. And so this region right here, where you have the mesh refinement at 3 layers, this is called the inflation region. Okay. Okay. Right, and so inflation will kind of give you more more options to kind of refine your mesh if you want kind of finer control. Okay, and so the kind of the area where you see inflation the most is actually in fluid mechanics, because when you're doing a fluid simulation, oftentimes you want to have a more refined mesh near the walls of your domain, because what can happen near the walls is a phenomenon known as boundary layers. And you want to make sure you have a refined mesh in your boundary layers to make sure that you capture things well. And so inflation is a great way to define that mesh, because oftentimes you have some kind of idea of how thick your boundary layer is, or how much it penetrates into your fluid flow. And so with inflation, you can kind of define exactly how many layers, how big the layers are, as you go through your fluid simulation. Okay. And so not that common in structures, but it has its uses too. Okay, and so when you see the inflation object in the ANSYS mesher, then you'll see kind of what it's used for. Okay. All right, any questions on this? Okay. All right, and so we have about 5 minutes left, and so that took a lot longer than I thought. And so I did want to start, because our next set of lecture notes is on nonlinear phenomena. Okay. And so I did want to kind of start it briefly just to kind of introduce the idea to you. And then on Wednesday, we'll really dive into it and really talk about it more. Okay. All right. Nonlinearity. Okay. And so up to this point, in the class, most of the time we've assumed our simulations have been linear. Okay. We've talked a little bit about what this means, right? And so we've talked about how, there's kind of 2 levels of this. And so on the first level, just the governing equations that we're using when we're doing static structural, this is just naturally a linear equation, right? And so the other level that we talk about linearity is with respect to the stress-strain relationship, right? And so what we say for a linear material is that the relationship between stress and strain is linear, okay? But for the purpose of this set of lecture notes, I want to be a little bit more general. And so, the whole idea with linearity is that you generally expect your simulation response to be directly proportional to the loads. Okay. And so if we do kind of a simple case with the cantilever beam, right? And so let's say that we apply a load of 1,000 newtons here, okay? And then what we measure is that the amount of deformation that we get is, let's say it's 1 centimeter, okay? Right? This is just kind of a very simple case. Right? If we assume that this entire situation is linear, and then we take the load and we cut it in half, right? Okay, and so let's say that we apply the same, we kept the geometry exactly the same. The only thing is that we took the load and cut it in half, right? And so instead of 1,000 newtons, we're applying a load of 500 newtons, okay? And so what linearity means is that, the amount of deflection that we get should also be cut in half, right? And so the deflection that we get is should be 0.5 centimeters, right? And so because we have the load, we should get half the response as well, okay? And so this is kind of more broadly, more generally what we mean by linear, is that, the response to particular, excuse me, the response to a particular loading is directly proportional, right? And so whatever factor we reduce the loading by, our response is going to be reduced by that same factor, okay? And that's true not only for the deformation, but also for the stresses as well, okay? And so in situation 2 right here, the stresses that we see in the beam are also going to be halved. Okay? And so when we have nonlinear effects, then this situation is not going to be like this. Okay. And so when we have nonlinear effects present, when we have the load, then the stresses and the deformations that we see are not necessarily going to be cut in half. Okay. And so what we're going to talk about, with nonlinearity is, what are the sources of nonlinearity? What actually causes this to happen in finite elements? And what can we do about it to make sure that we accurately model these things? Okay? Because in reality, most structures, their stress-strain relationship is going to be nonlinear, right? And so nonlinearity is a fact of life. But for a lot of situations, we can either assume, kind of correctly assume that linear behavior is there, or we can take certain steps to make sure that we capture the nonlinearities exactly. Okay, and so that's what we're going to start talking about on Wednesday, and then probably we'll continue that, into the following weeks. Okay. All right. Any questions on this before we wrap it up for today? Okay. All right. So that's all we got time for. So thank you everyone for tuning in. I know it's kind of a busy week for everyone. And so I'll stick around after class for a bit to answer questions on your midterm projects. But if you have no questions, then you're free to go. So have a great week. Have a great evening, everybody. And if I don't talk to you after class, then I'll see you on Wednesday.
Hello, Professor.
Yep.
I have quite a few questions for Ryan.
Sure.
Well, I mean, not that many, I guess, really, but I'm having trouble finding like materials and stuff.
Mhm.
So, and also that, like, you remember how the geometry is for the, it's like this or whatever.
Yeah.
And it's got this thing coming up right here.
Yeah.
So like this isn't actually a support. It's like normally there would be a I don't know what you call it, whatever, a wheel,
Mhm.
and then there's a stopper here, and then like, so it goes in like this,
Yeah. Mhm.
and it blocks the valve.
Mhm. It's a plunger.
Yeah, so I guess my question is like, wouldn't this significantly increase the pressure here? Like this way?
It would. Yeah. So when the valve is closed, it's you definitely have much higher upstream pressure than downstream. Because you have fluid coming in and it's just hitting the stopper. And so you have much higher pressure. You have almost no pressure downstream.
Yeah.
Yeah.
But I mean, we can't move this on the geometry.
You can't, but you can model the effect of different pressures on different faces. And so you could select all these faces up here upstream and apply a higher pressure from there compared to downstream.
Yeah, but the thing is that I have no idea, like, the pressure at all.
That would be the difficult thing. So to really get a sense for that, you have to run kind of fluid simulation on that. But I think one kind of naive way that you can do it is that you can apply just your pressure boundary conditions upstream, and then downstream you can just have no pressure.
Yeah, I mean, definitely, I see that. But my problem is that, like, right, so we're modeling it. And like one of the things I wanted to do is say like, okay, what's a safe operating pressure when this thing is open?
Yep.
Except the safe operating pressure when this thing is open is going to be dependent on what's the pressure that results in the top half when this thing is closed.
Mhm.
Because like, So like, let's say, for example, we have like, I don't know, I saw one that was rated like 0 to 20 bar, right?
Mhm.
And so I'm assuming that this 20 bar is its max pressure that it's able to safely handle in case it needed to be turned off in an emergency situation. That's what I'm assuming.
Yep. Mhm.
So, but like, so in my calculations, if I'm just, doing a factor of safety of like 2.3 or whatever, right?
Mhm.
And I say, okay, so the most that you want to run, this given geometry on with this material, blah, 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 is, I don't know, what's one bar is what, 100,000 pascals.
Mhm.
What's that? Is that 1 kilopascal? Or 1 kilonewton? Or is it
It's 100
pascal?
It's 100 kilopascal.
100 kilopascal. 100 kilopascal. So let's say 1,500 kilopascals is what I get, right?
Sure.
But then how do I know what the pressure is going to be here if I suddenly close this?
Mhm.
It's not just going to double, is it?
No,
No.
right. You have
So
to,
like,
you
how
have to,
do I know that this is not going to be 2.3? It's going to be more than 2.3 times.
yeah. Unfortunately, that depends on what the speed of the fluid is going through it at the time. And so, then that's kind of beyond what I'm going to ask you to do. But I think as a reasonable approximation, I think you can say that it's going to double. And I think that's fine to do. Given the constraints of what you have to work with right now, because in reality, you would do run the fluid simulation on it. And first, and another thing too, that you would have, say you're actually designing this for an actual plant, you would actually know what the velocity of the fluid is going through that. Right now, it's all kind of made up. So you can put a velocity there, and that's fine. And actually, if you do add a velocity, you can compute how much the pressure would rise. You can just do a very simple Bernoulli equation calculation. What you have is, if we ignore gravity, you have pressure divided by density plus 1/2 times the velocity squared. This has to be constant in a fluid under some situations, but it's fine in most cases.
Yeah, because I was seeing some complicated equations for the change in pressure on some websites that I was looking at. I just wasn't sure how that would affect this.
Yeah, and so if you have one situation where the valve is open and the fluid's going with a certain velocity V1, then in situation 2, this is gone because when you close the valve, you're going to create a stagnation with the velocity is 0. And so your net pressure here is going to be the sum of what the pressure was beforehand, plus this extra kinetic energy term for the movement. And so that's one way that you can estimate it, but then you have to kind of, for this project, you would have to estimate what this is and what this is, which I think is a little bit beyond what I'm asking to do in this project. And so I think, one approximation you can make is that this term and this term are roughly equal in magnitude, which is not a bad approximation. Then your ending pressure P2 is going to be double what you have.
All right. Yeah, because I was just concerned when I was thinking about it today because, I guess my results would only be good if this thing was open and you didn't have to shut it.
Right.
So
I think it's fine to make an approximation.
all
I mean, you're going to just naturally, you're going to have to make, a lot of this project is imagination, imagining certain scenarios and how they work out. I think this is within the realm of what you can, as long as you can justify it and say that, I'm making kind of, because I don't know this, I don't know what the working pressure is or what the velocity is. I'm just going to assume that the pressure doubles. I think that's reasonable. That's reasonable.
all right. So if I so in reality, if I wanted to have a safety factor of 2, I would need a safety. Is that even good? But I don't know. I just think, is that good in a situation like this, a safety factor of 2? I mean, I guess
I'm
it
actually not
depends.
sure.
I guess it depends how critical this is
It
to
is.
whatever you're doing.
Yeah.
But so then, if I really wanted to have a safety factor of 2, I would need a safety factor of 4 when it was open. If I'm just going to assume the pressure doubles.
Yeah.
So I would need the safety factor up here to be 2. And then also,
I'm having trouble finding material data. So, because I've been looking up, Conwell told me a couple materials, and I did use malware, but I don't really know how to use it very well. So he told me like some stainless steel options.
Okay.
But I was looking up its applications in its aerospace, and so I'm seeing that there are some stainless steel glow valves, but a lot of the times they use what do you call it, cast iron. But that's only, they said it's for low temperatures and low velocities, low-ish velocities, because it's not flexible at all.
That makes sense.
Apparently, so like, I don't know, what do you call it? Ultimate strength.
Yeah.
Is like, what is it when it does the graph? When you have your graph where it's like, okay, yield strength is here, and then you get more into plastic deformation.
Yeah.
Oh, it's I don't know the exact term. I think I know what you're talking about.
Okay, yeah. So apparently it's really extremely rigid. So if you have any deformation, it's liable to break. So they use cold press, or I mean not cold press steel, cast steel instead of cast iron. But I don't know what the name of the cast steel is that you would use for globe valves. So I can't find it. I can't find its material properties in any type of database because I just don't know. And then also like a lot of these, you know, I'll have to look up a diagram of like what these different parts are called, but like I think that like some of these like bushings and stuff, like this might be copper or something like that. So there's gonna be multiple different materials, and I'm thinking I might just leave those the same. So I'll do one cast steel and maybe one stainless steel, but I'm just gonna change the body because I think that that's where all the deformation is gonna be happening.
Yeah, that makes sense to me.
But I just don't know where to find the material data on the cast steel that I need, or like what it's even called.
If you can't find the materials, you can or the specific properties of what you're looking for, you can kind of like you've read about how it generally varies from steel from other types of steel, right? And so you can apply you can kind of make up properties. So I think that's okay for this sense because even I don't know that stuff, and so I can't grade you on how accurate you are in estimating the properties for cast steel.
Okay.
But if you say that in general we expect cast steel to be more flexible, lower Young's modulus and things like that, you kind of have a realistic decrease, maybe like 20% or something like that. I think that's justified. I think that's a reason. That's another kind of reasonable assumption. Yeah. So it's all about it's you're going to have to make a lot of decisions like this, and so as long as it sounds reasonable based on what you've read, and you can kind of justify that, then that's most of it. A lot of this stuff I honestly can't verify stuff like what the factors is, what the velocity is and stuff. As long as you're saying that you're actually accounting for this and you're thinking about these situations, which is what I want you to do, and you have kind of a way that you can justify the numbers of what you put in. That's what I'm going to do. That's what I can actually assess.
Okay. Sounds good.
Yeah.
All right. Thanks, Professor.
Yep. Are there any people here? Manuel, did you have any questions? I'm going to go make a round around the classroom and then I'll come back. And so if you have questions, just kind of stick around for a while.